This next problem is a little more complicated. So this is the one where you have a father pulling his daughter uphill on a sled. So you have to read the whole problem to identify that uphill, there's an angle associated, so there's going to be different things that go on with the solving process. You also have to recognize that there is a coefficient of friction, therefore friction is going to be involved in the situation. The problem also says constant velocity. So from all the things that you know, constant velocity is a sort of equilibrium, and that means that there are no net forces acting on the object. So for our purposes, that means all of the forces are going to end up canceling out, which means forces directed to the right are going to equal forces to the left, forces up are going to equal forces down, and vice versa. So what we know that we have a mass of the daughter of 22.7 kilograms, and then we have a mass of the sled of 3.18 kilograms. Now those two objects together become a system, and that system isn't going to change. So what we can do is add those two masses before we do anything else to get the mass of the object that we're actually dealing with. So we would take those two numbers, add them together. That's going to be the mass that we're going to use for all of our problem solving. We continue reading, and it says that we have a coefficient of kinetic friction of 0.212, and we have a coefficient of static friction of 0.317. Now the problem says that it's moving at a constant velocity. So you should know already that if it is moving, it has overcome static friction, and the only friction left is the kinetic friction. So that is why we can disregard the static friction coefficient and only work with the kinetic. The question wants us to know how hard the father has to pull in order to keep it moving at a constant velocity. And then we're provided the angle of 15.5 degrees. All right, so the first thing that we have to do is draw our free body diagram. So we're going to take this person, make it a box just for the free body diagram, and we're going to address all the forces acting on it. So the easiest one is always that we have gravitational force pointing straight down from the center of the object. The next force that we always have is the normal force, especially if it's on a surface. In this case it is. And that force has to be perpendicular to the surface of the ramp. So we have our normal, we have our FG. Problem gives us coefficient of friction, so that means that we have to have a force of friction. Now in this problem, she's being pulled up the ramp, so that means that the force of friction is directed down the ramp. Friction is always going to oppose the motion. And then finally, we're going to have a force of tension, or an applied force, which is going to be directed uphill. Now, as it stands right now, we have to identify which forces are acting and which ones cancel out, all that jazz. So the person on the sled does not leave the surface of the hill. So that means that the perpendicular components to the hill are going to cancel out, which is our Fn and our Fgy. Remember, we have to rotate our axes when we're doing ramp problems. So Fn equals Fgy, which is going to be important when we get to the force of friction. Now in the x direction, or the pseudo-x direction, we have the pull force directed up the ramp, we have the frictional force directed down the ramp, and we also have a force of gravity directed down the ramp. So the gravitational component is going to be directed on the ramp, but backwards. So what that means for this particular problem, since we know that it's a constant velocity, we know that the rightward force has to equal the leftward force, equal and opposite. So that means that the pull force up must equal the gravitational in the x direction plus the force of friction down. So we set up that relationship and look at what we know. We're solving for the pull force. We know the formula for force of friction is coefficient of friction times force normal. Then we know that Fgx on ramps is always mg sine of theta. So we have all that put together. When we look at our force of friction is coefficient times force normal. Normal in this situation, because we're angled on the ramp, is equivalent to Fgy. Fgy is equivalent to mg cosine theta. So we will plug in, and ultimately what you end up with is that the force of the pull is equal to coefficient times mass times gravity times cosine of theta plus mass times gravity times the sine of theta. And that's going to get you your value. So ultimately, when we put all that together, we end up with a value of pull force of 119.59 newtons. Right now, the girl's weight by itself, the girl and the sled together, are over that 119. So the ramp in this case is helping because he does not have to overcome nearly as much force as if he would if it was a vertical move. which makes sense because when you pick something up, you have to work directly against the gravitational force. When you pull something up a ramp, you only have to work against the force of gravity that's directed along that plane, which is why ramps and levers and all that jazz are examples of simple machines. They reduce the amount of work required to make something happen. All right, that's the end of that problem.